Okay, so a bit more on about the Bayesian data analysis third edition book. On the chapters we did not go through, a bit of kind of what chapters specifically have something useful and also what is missing in some of these chapters. Overall, it was kind of that this BDA third edition had been in progress for already some time before I was asked to help with that. And at that point, there was a pressure to get it soon out. And I think that it's and afterwards, it happened to be in kind of the transition phase that we could have included a bit more on Stan, but also Stan wasn't that mature right away at that point. And so now we can see that even if it's the book has a lot of useful information, there are many parts where specifically the computation is referring to bit kind of outdated things. And so when reading it, need to be kind of that you can pick parts which are interesting, but you can also then skip some of the specifically the computational discussions. This chapter 8, I highly recommend reading through it. The reason why I did not include it in the course, even if like some years we have this 12th lecture, I could go through it. It's very dense in a way that it has a lot of information. So it is also difficult to go quickly through it. The important part is that in a way all the examples before that, it was assumed that we just make the model but not specifically think how the data was actually collected. And then chapter 8 discusses that why sometimes we don't need to model specifically how the data was collected, and then we say that the data collection is ignorable. So we can ignore that part. But then it discusses many different cases where the data collection is not ignorable, and we need to model also that part, how it was collected. And so this is very useful chapter to just also know different cases where the data collection is ignorable or is not. And then if you remember that, you can then come back later to read details of these different cases. And so it specifically has then discussion on sample surveys. So you have some population of, for example, people, and then you ask question only from some of them. The typical is these election polls. And the problem is, of course, that it's not possible to do complete random sampling because you can only reach certain people, and it's also getting more and more difficult because at the time of landline phones, people did answer phones, and it was more easy to get more random sampling. Even then, not everyone had phones or were that much home. Now with the mobile phones, it's more likely people don't answer if there's unknown number calling, and kind of how we can take into account that we reach only certain population, but we know about the demography background of those we reach and demography of the whole population. Design experiments, like in medical experiments, that we can actually choose what the treatment is. And the randomization there also, that how we can then choose who gets the treatment. It's not just the doctor would decide themselves. The randomization helps there also to make part of that data collection ignorable. Observational studies are common for specifically for these kind of long-term, like what people eat. It's difficult, and smoking. It's difficult to make controlled, designed experiment where you would randomize that, okay, now you are going to smoke a pack of cigarettes next 30 years, and then we check how healthy you are. And then observational studies just asking that, okay, that you've been smoking 30 years, but now it's difficult to know what other choices they made. Censoring and truncation, that you might have, censoring is typical in these survival analyses, that we give some treatment and then we, instead of just checking that who died and who did not die in certain time, we get more information if we look how long did they survive. But at some point we want to also publish the results, and then we know that there's a kind of censoring that, okay, they survived up to this time point, but we don't know when they would have then died if we would have followed longer. So it's a censored event. Truncation is also possible when we measure things from blood, for example. There can be that there's some minimum smallest value that it's detectable, and in a way that we are then truncating to the smallest values, or there can be the highest value also that they kind of saying that, okay, our scale can't tell higher values. There's a chapter 14 to 18 overall are about regression. They go deeper into details, but it's also these chapters specifically have almost like half of the material is discussing that kind of computational issues. We don't need to care anymore with probabilistic programming and with, for example, STAN. And then half the material is then something useful and interesting also for you to read, but then in many cases it's also that it's a bit briefer, and there are then other books going in more details. So chapter 14 has also this justification of conditional modeling, why we can just model the path outcome variable given the covariates. Why don't we need to model the distribution for these covariates? This was also briefly hinted in the exchangeable part in their discussion on that, but there was a kind of additional justification for this. The chapter has discussion of Gaussian linear model with conjugate prior, and then it happens that the conditional posterior is multivariate normal, and you know that from chapter 3. If we have, in addition, fixed prior on weights but unknown noise variance, we get joint posterior, which is normal inverse chi-squared distribution, which was also mentioned in chapter 3. But then already if we have both unknown noise variance and unknown prior scale on weights, then we go beyond fully conjugate case, and then there's discussion of Gibbs sampling, but of course now you would use just probabilistic programming and MCMC. Of course, these kind of these computational issues, sometimes they still can be useful to know, but it's more likely if you are developing yourself solutions for some specific case where the computation speed is important while with the probabilistic programming it's faster just to write the model, and then even if the computation is not the fastest possible. The speed on causal analysis, also in chapter 14, useful to check, but not much. ROS is the regression and other stories coming out in the beginning of next year. There's already the older edition is available, but this has then several chapters on causal analysis and overall regression. There's assembling matrix of explanatory variables. You probably have had in other courses about the feature selection too, and briefly discussing identifiability, collinearity, which leads to these posterior dependencies, like in the body fat example. Nonlinear relations, so you could just make a nonlinear transformation of some covariate to get nonlinear relations, while still the model is linear with respect to parameters. Indicator variables, categorical variables can be included. Interactions, typically in linear models, this interaction is just multiplying things. Specifically, what BDA tree is missing is variable selection. There's not much discussed, but then you can see lecture videos 9.2, 9.3, and the material I referred there. There's a lot of variable selection and the kind of my recommendations how to do that. Regularization is not much discussed. Again, see more lecture 9.3, and there's also this case study is good about the connections to. Someone asked specifically about Lasso, and I will say about that soon here also. And there was in chapter 14 also unequal variances, correlations, and these are also now with the probabilistic programming easy to include. So someone specifically asked the connection between Lasso and Bayesian Lasso. So Lasso is penalized maximum likelihood linear regression with L1 penalty, where the amount of penalty is adapted. So L1 penalty in the corresponds to having then this double exponential or Laplace prior, so it's more peaked at the mode, and in the log space looks like this. And kind of the idea would be that, okay, we assume that it's more likely that there's more mass near zero than compared to Gaussian. In this original Lasso, because it's using this penalized maximum likelihood, it finds the mode given the penalty parameter, and this finding the mode of the penalized maximum likelihood is kind of the same as maximum a posterior, but it's important for the original Lasso, this mode finding. And then when we are combining this kind of prior, and then we have from the likelihood something which can be kind of uncertain, when the prior is, or the penalty is weak, it can make the penalized likelihood something which has some bump here, but then it stays convex. It can have slight kind of bump here, but still the mode stays there. When the penalty is increased, correspondingly prior would get more narrow, and eventually there would be then peak at the 0, and then when we go to the mode, we get these exact zeros there. And then the Lasso algorithm starts with weak penalty, and then increases the penalty, and then kind of checks that when each of the coefficients, the mode of the coefficient gets to 0, and then eventually one by one these coefficients get to 0, and one by one each covariate is removed from the model. And then, of course, marginal modes of weak effects go to 0 first, and so the most important ones tend to stay there. But this has also that when we have dependent parameters, this removing weaker things first, it tends to remove also weaker correlating variables, and then leaving less correlating variables in the end. However, when the amount of penalty is increased, also the relevant coefficients are shrunk towards 0, so that's not good. And then sometimes relaxed lasso is used, so after finding which variables to include, then do just weak L2 penalty regression estimation, so corresponding to using weakly informative Gaussian prior. Now then, someone thought that, okay, since Lasso works so well, and since Bayesian is so great, combining two good things has to be better. But it turns out that now combining two good things is actually worse. So the L1 penalty is same as using the Laplace prior, but now we are looking at the whole distribution and not just the mode. And that posterior doesn't shrink to 0. We are still integrating over that posterior. When we are integrating over that posterior, it will have non-zero effect on predictions. And so we don't get that sparsifying effect using Laplace prior and Bayesian lasso, and the tails go down too fast, it's shrinking the bigger effects too much, and especially if we add more and more covariates, it works worse and worse. And both theoretically, it's reasonable to use, if we assume that only some of the covariates would be clearly away from 0, it's better to, and also then empirically has been showed that better to use more sparse priors in a way that they have even sharper spike near 0 and even longer tail. Having thick enough tail helps that the peak effects are not shrunk towards 0 at the same time as it's shrinking the smaller more strongly. It's also best to separate selection of sensible prior. What prior would reflect our information, how many covariates are relevant, make a good best possible posterior inference for that, and then afterwards do the decision analysis which variables are important or useful to make predictions in the future. This is from Carvalho, Paulson, Scott paper. This kappa on x-axis is now how much each coefficient is shrunk towards 0. So there's 0 shrinkage. We would like to have a 0 shrinkage for the relevant variables. And kappa 1, there's a full shrinkage, So irrelevant variables, we would hope that they are fully shrinked towards 0. And you can see the Laplacian, it has some density to 1, so it is saying that some of them are shrunk heavily. But it doesn't allow, it is shrinking everything. So there's no prior mass for case that some of the variables are not shrunk at all. And then horseshoe is now what I recommend then if you want to, if you have a prior information that only some of the variables covariates are relevant, because then it has spike there that a lot of posterior mass for those that shrunk completely, and a lot of posterior mass don't shrunk at all. And actually instead of the old horseshoe, I recommend regularized horseshoe, where we have additional parameter deciding how much do we shrunk also the big. This is useful when we have many variables. We actually want to also, a noisy target, we want to also shrunk a little bit those largest, and then we can control that or integrate over that uncertainty. And just to illustrate, compared to Lasso, so traditional Lasso here, reference model is Bayesian model, which has all the variables included. Integrating over all the uncertainty is a good thing. There's a Lasso path. So increasing penalty, we get smaller and smaller models, and then when we start to remove too many, the mean square error starts to increase. And we would like to then, in a Lasso, choose something along 10, 15 variables. But it's worse than the full Bayesian model. Here's the relaxed model. We can get actually a bit smaller models because now we are not shrinking the relevant variables that much. But still, we can't reach the full Bayesian reference model, even if we can get to smaller models. And here's the projection predictive approach, which can reach the performance of the full model, and then it's just by chance that it can go also below. But anyway, we can get much better results using Bayesian inference to make first sensible full model, using good priors, and then doing the decision tasks separately. Just the log predictive density plot there too. Okay, I'm going a bit over 4. So free to leave if you are busy. Chapter 15, hierarchical linear models. Since you know hierarchical models, theory is easy for you. The book chapter discusses a bit of computation, but again, with probabilistic programming, computation is easy. There's specifically one section which discusses transformations for HMC, centered versus non-centered parameterization, which is relevant. And there's a bit more on Stan user guide about this reparameterization making HMC more efficient. It's useful to know the terms fixed, random, and mixed effect models. We don't recommend actually using them, but it's just that they are so common that it's useful to know them. It's also annoying that they are used with different definitions, so it's sometimes confusing that what's actually meant here, that they are not always used consistently. And examples are that fixed effect refers to something that we would say is a population effect. So the first one where we have all the groups have just one coefficient, and we could say also that then this is the pooled model. It's kind of, for me, it's kind of strange that when I hear fixed effect, I think that it's something that's actually fixed to specific value, but it's still something which is unknown. So I find difficult to think about the term fixed. But it's just, if you remember that, it's actually kind of the population effect. There's random effects. If you have group-specific effects, again, it's kind of strange that why they are random, because they can be also actually deterministic differences, but just unknown differences. And instead you could say group effects, group parameters. And if you combine fixed and random effects, it's called mixed effects model, which would be just hierarchical model in language used in BDA. There's also ANOVA model in section 15.6, but you can also do using, for example, Arst and ARM has the stan underscore AOV. Chapter 16, generalized linear models. The Bayesian model is an example of generalized linear model. You already used that. And so the components are, we have some linear predictor. Eta is combined linearly from the this covariate matrix. There's a link function, some nonlinear function that transform then eta to mu, and that mu is then location parameter for some outcome distribution. Originally, it can also depend on dispersion parameter, this outcome distribution. Originally, this was just for exponential family distributions, like Poisson, binomial, negative binomial. The exponential family distributions are special that they have this natural parameterization, which can kind of that you have natural way to have the location parameter and dispersion parameter for all of these distributions. They had also the benefit that they are also log concave. The likelihoods are log concave, so computation was also then easy. But then after MCMC made the computation easy, people call also models where the outcome distribution is not part of the exponential family, or also if the dispersion parameter have its own latent linear predictor. These kind of things are also nowadays called generalized linear models. And of course, hierarchical GLM is natural extension. The 16.3, it's an excellent discussion of weakly informative priors. It has, it's good to check after reading that section, our prior choice recommendations wiki, because we've changed our opinion on Cauchy since the book was published. But otherwise, it's overall going to be good discussion and good examples on the how to think of these. Chapter 17, models for robust inference, just replacing these outcome distributions with something which has thicker tails, so it is less sensitive if there are outliers. And of course, it can be sometimes that it's not actually outliers, it just is that the measurement process has thicker tails. So it's kind of that these are often used assuming they are outliers, even if they could be used because it's not specifically outliers, but the distribution just is more thick-tailed. And then computation with MCMC is easy, so computational discussions in that chapter are again a bit outdated. Posture can be multimodal, which makes the otherwise the computation a bit more difficult. Arst and ARM doesn't have the distribution for outcome, BRMS has, so it's easy also if you're using those, the one-liners. Chapter 18, models for missing data, extends the data collection modeling from chapter 8. Lot of useful terms for missing data. specifically missing completely at random. So the missingness does not depend on missing values or other observed values. The missing data typical would be when we collect medical data, some of the measurements, so not all the people have all the measurements, medical measurements, so we have missing information. And now if it's completely random, it doesn't depend on, for example, how sick that person was, or it doesn't depend that it's missing because it was below detection threshold. That would be missing completely at random. Missing at random is such that it does not depend on missing values. So again, if it would be depend, for example, going beyond threshold, it would depend on that missing value also, but it might depend on the other observed values. So we might be able to predict, based on other observed values, that some data is missing more often, for example, for females or more sick people. And then missing not at random. The missing net depends also, for example, that we are missing more often below threshold, or specifically we measure something only when it's also giving symptoms for the person. Multiple imputation. Make a model predicting missing data, which is then easy with this missing completely at random or missing at random. Sample repeatedly from the missing data model to generate multiple imputed data sets. And then these are kind of your posterior samples of data sets. Then you can make a usual inference using each of these imputed data sets, and then in the end combine results. And so this multiple imputation is the commonly used approach, because you can after imputation make the inference as usual. And of course there's a lot of literature then how to do these models when we have these missing and random, and we need to take into account these dependencies and so on. Final thing, maybe 5 minutes more if you endure. Gaussian process is infinite dimensional extension of normal distribution. It's very useful prior for nonlinear functions. The nice thing is that even if the process itself is infinite dimensional, when we are interested in any finite number of variables, the marginal is multivariate normal. And you know from chapter 3 that multivariate normals are easier. We can have the analytic equations for conditionals and marginalization and so on. And we usually then have the kind of that it's so multivariate normal has then multivariate location and multivariate and the covariance matrix. Often we start that a priori location, so that we have the kind of zero-centered Gaussian process, and then we have the covariance matrix composing of terms which can produce, for example, smooth nonlinear functions like this. So if we think that we have here x and we have here f, and if we start that we have 0, marginally, if we look at it just how it looks like f at x1, it's, since we look at just at one variable, it's just univariate normal. If we then think about that we want to also know how it looks like the distribution for at 2 points, oops, x2. So at x2 it's also this normal, and these are now just prior. But then we can look also jointly. So we have then fx1, fx2, and now we can make it more interesting if we say that there's some correlation between these, so that if function value at x1 is high, then function value at x2 is also high. And we can make this correlation such, as in the example there, this correlation is such that when the distance increases, so we have a correlation 1 at the 0 distance, of course correlation 1 with location itself, and then it gets smaller. So if we then know that, okay, f at x1 has certain value, then we know that because there's a high correlation very nearby, then any function values here nearby have to have conditionally quite narrow distribution. And conditionally on this point, further away, they can have wider and wider distribution. So this gives us smoothness assumption. Here are examples we draw from this kind of prior. So we can start drawing one value, and then we can draw conditionally the next value. And if we draw these values close enough and connect them with line, they look like smooth functions, but they are still evaluated only in finite number of points. And then if we randomly choose from each of the conditional Gaussian, then they can randomly move around smoothly. I can show you animation. So this has been made by Tomi Peltola, who's graduated from Aalto and was a postdoc at Aalto also. Now I think he's at Curious AI. We can repeat this sampling, and so it is. You can always think that it's first sampling the first point, and then many points that conditionally always how these are correlated. So nearby values have to be really close. Further away the points are, less correlated they are, and it's more difficult to kind of predict that if you know value some point with the other one. And these are now just draws from the prior for functions. And it's possible then to have different priors so that we can make them smoother. I can add another. So there's now sampling from two different. One is much smoother than the other one. And there are also otherwise possible to have much less smooth functions depending on what are these covariance functions. So also very ragged functions. So and also periodic. So you can see the green one, it has let's see if I can remove some of these. This one and this one. So you can see the periodic one. It has a repeated pattern, but otherwise in that one period the shape can be anything. And then remove also then the periodic one. And then we can add also observations. And now, when we add observations, we now condition that these different functions need to go close to those points. There's some noise allowed, so they don't need to go exactly there. I can add more observations, so I'll add a bit more. So it's still here. Let's add a bit more here. So now, since there are several observations close by, you can see more clearly that they are staying nearby those, but otherwise still there's a lot of freedom between. And I can add now a bit more. Let's make this kind of curve here. They are still, it's possible to explain these dots. There's that much noise with many different, and we can add, let's add another different, let's have less noise, longer length scale, smoother functions. And you can see the green one is now smoother going through the points. And here are also examples where, with the different length scales, they've been conditioned on the data. So we have a prior on function space, and we can add data to learn different nonlinear functions. Conditional on this covariance function parameters. So we had one parameter which was the length scale, how quickly it varies. One was the magnitude, how large variation there is. Conditional on those, the posture is just multivariate normal and everything is easy. We need to usually also make the inference for covariance function parameters. So how smooth, when we get more and more data, we can also learn how smooth the function is and so on. We can do this when we have a Gaussian process prior on functions and Gaussian outcome model. Everything is Gaussian, and we can compute marginal likelihood for these covariance function parameters, and it's relatively easy. Only thing is that then it scales cubically with the number of observations, which gives some challenges for bigger data. Here's an example of additive model. This is something like what also Prophet and what Mikko talked about, kind of different components, and it's also from the BDA cover. The number of pairs or relative number of pairs, and then divided in components in long-term trends, weekday effect, seasonal effect, special day effects. And it's easy to make this kind of that each of these additive components has different smoothness or length scale assumptions, and some of them have periodicity, coded there because we know that we have a 7-day week and we know that we have 365 and quarter days per year. Actually, then adding leap day is a bit complicated to make this really good, but it's otherwise easy to add these components like this. If we have a non-Gaussian outcome model, here the example is survival model, and survival times are always positive. This was log logistic model, and then it's a similar extension as for these generalized linear models, and here we've been able to find also nonlinear effects, especially this white blood cell count effect there. Last slide. There are these GP-specific software like GPy, GPflow, GPyTorch. I had also and it's still existing GP stuff, but since it's in MATLAB, I don't develop that anymore. And now it seems that most of these efficient software are in Python. And these GP-specific software can take into account so many different things related to GPs and use certain approximations, and they scale computationally much better than Stan, which has this more generic approach. It has some built-in covariance functions now, so it is getting at least some speed up and soon GPU support. But like Stan and GPs are specifically useful when you don't have much data and you have a lot of structure and you want to experiment with the structure. These GP-specific software then usually have much more limitations in the way that what kind of models you can implement, and they are just fast if you stay with the basic models. In case of non-Gaussian outcome models, sampling of latent variables can be slow. Again, to get in the faster models, we are getting this Laplace integration of the latents coming, and last week I talked about Laplace approximation, and now we are just doing integration over the latent variables with the Laplace, and then MC for the covariance function parameters, and that combination then is useful. Okay. So that was the last slide for this year.